This video we're just going to review the ions that are formed by different elements in the periodic table. And we can kind of make these broad generalizations based on group. And remember that the group that the element's in, which is kind of the column, tells you what the valence electrons will be like for that element. And those valence electrons, remember, are just the kind of the highest energy electrons, so the ones with the highest energy level. So if we just look at sodium, for example, and we take, let's see, we'll look at this row right here as we go across. Right, so sodium will end in S1, then magnesium S2, P1, P2, P3, P4, P5, P6, right? So if we look at sodium, here's its electron configuration. We're saying if it lost its 3s1 electron, it would now have one more proton than electron, so it would become an ion, sodium plus 1, and it would have the electron configuration of neon, which is super stable, because now it has a filled 2s and 2p orbital. And then once it's reached that state, there's kind of no more stable configuration it can have, so it's going to stick with that configuration. Magnesium, if we removed the 3s2 electrons, so now 2 electrons have to go, we could get to that super stable neon electron configuration. But if we're losing 2 electrons, it would give magnesium a charge of +2. For aluminum, if we moved the 3s2 3p1 electron, it would have a +3 charge, and it would have the electron configuration of neon. So in general, groups 1a and 2a form +1 and +2 cations, right? Cations means positive ions, respectively. And 3a can form +3 ions. Groups 4a and 5a, they're kind of in this awkward in-between, because to remove 4 electrons from something to make it a +4 ion is really hard, right? To just kind of take all those electrons off, it gets harder and harder to remove those electrons. Conversely, if I wanted to add 4 electrons, that would also be hard, right? And the same is true for 5a. Either I have to take away 5 or add 3. Both is kind of just energetically, it's too much. But once we get to 6a, we can see a parallel with 2a. 6a needs 2 electrons. And if it gets 2 extra electrons, it'll have the electron configuration of argon, right? Super stable, filled 3s2 and 3p orbitals. And once it gets to that electron configuration, it won't tend to change. And that would give sulfur a -2 charge, which is now an anion. Anions because it's negative. Chlorine only needs 1 extra electron, so it would become chlorine -1, a chlorine ion. And it gets the electron configuration of argon, which again is super stable. And so we can kind of say in general that, 6a and 7a elements will form -2 and -1 anions, respectively. And that once they get that configuration, they'll be very stable. 8a, well, these are the ones that are already really stable, right? These are kind of the role models, if you will, for the other atoms in terms of stability. So 8a elements don't form ions because they're already really stable. And there's kind of no reason that the electron configuration would change. So what we're going to start talking about in the next video, and I'll kind of prime you for that, is, okay, we're kind of talking about these electrons magically disappearing or magically being added, but like, where do they come from and why would that happen? What I'll leave you with is, well, sodium wants to give up an electron, and by one, I mean it would be more stable, it would have a more stable electron configuration if it lost this electron. Chlorine would have a more stable electron configuration if it gained an electron. So both would be more stable if sodium lost one and chlorine gained one. And that's going to be our intro to the ionic bonds in the next video. And an ionic bond is basically that transfer of an electron from a sodium atom, for instance, to a chlorine atom that would make a +1 sodium ion and a -1 chlorine ion. And remember that positive and negative attract. And so those two ions will start sticking together.